A very good evening to you all. On behalf of Surendranath College, I welcome you all to this one-day national webinar organized by Department of Physics under the DBT-Star College Strengthening Scheme. Today, we have with us two bright minds, two young scientists from IIT, who are going to unravel the mystery of the dark universe. Now, the topic has garnered overwhelming interest, and as a result, I'm proud to announce that we have 639 registered participants for this webinar who are going to view to this webinar, listen to this webinar from in Zoom as well as in YouTube Live. So without much ado, now I would request our principal, Dr. Indranil Kaur, to inaugurate the program. Over to you, sir, Dr. Indranil Kaur.
Thank you, Aditi. Today, it's a real pleasure for me to come to this platform to inaugurate a unique webinar where we actually unveil certain secrets of the universe, which Professor Hawkins used to excite us by his statements and his publications on and off. It is really true that the universal mystery still remains, though we have unveiled a pretty small part of it, but still the entire universe is a mystery, and I feel today's exciting lecture will unveil a lot of it and excite the young minds in the platform today and make them feel their existence and also the rule of law in the universe. Thank you very much. And with this, I hand over the mic to the organizers for conducting the webinar. I wish it's wonderful success today. Thank you.
Thank you, sir. Thank you for your support. You have always been supporting in all our ventures. Thank you. Now I would request Dr. Ashok Kumar Das to introduce our first speaker. Over to you, sir, Dr. Ashok Kumar Das.
Thank you, madam. Good afternoon, everybody. It is a great opportunity for me to introduce the student's first speaker in this webinar, organized by Department of Physics under the DBT-Star College scheme, Government of India. Our first speaker, Dr. Subhaditya Bhattacharya, did bachelor and master's degree in physics from Jadavpur University, Kolkata. He obtained his PhD in practical physics from Harish Chandra Research Institute, Allahabad. He was a postdoctoral fellow in University of California, Riverside, and after that, he joined IIT Guwahati as a permanent faculty. Currently, he is working there as associate professor. Throughout his academic journey, he has published 38 research papers in international journals. His research interest currently focuses in dark matter and its implications in direct, indirect, and collider experiments. He was awarded DST Inspired Faculty Award and recently got DST Sarkar Research Grant from Government of India. We are fortunate enough to have him as our first speaker of today's program. So I wholeheartedly welcome Dr. Subhaditya Bhattacharya and request him to deliver his lecture on In Search of Dark Matter. Over to Dr. Bhattacharya. Please start your presentation.
Well, so thank you so very much for this very kind introduction and for this invitation to allow me to speak about the dark matter searches in this webinar. And so before we start, let me try to share the screen, and you need to tell me if everything is visible and you can see the screens.
Yes, we can see the screen.
You can see the screen, right? So, all right. So without further deliberation, let me start then. And so the title of my talk is In Search of Dark Matter. And the plan of the talk goes like this, that I will start with the evidences of dark matter that we have accumulated so far. Then I will talk about some broad features that this dark matter particle in general should consists of. Then I will come to the experimental search strategies for this dark matter particle in different ongoing and future experiments. And I will end with some concluding remarks. All right. Okay, so let's start with the evidences of dark matter. So it all started around in 1933 when a Swiss astronomer Fritz Zwicky was studying radial velocity dispersion of galaxies in the Coma cluster. Now, what he used was the virial theorem, and let me try to explain that very briefly. You all know perhaps Newton's second law, which is Fi equal to mi d2 ri dt2. And now you can recast this equation to write it in terms of half of double derivative of mi ri square equal to ri dot fi plus mi dri dt whole square. Now you note that on the right hand side there are two terms. One is ri dot fi, and this is precisely what is called the virial. And the second term is actually twice the kinetic energy, which we all know that this is half of mi vi square, where this index I is essentially referred to the different galaxies in the galaxy cluster. All right. Now, if you take a time average and you assume that the distribution of the galaxies in the cluster do not change much, then the left-hand side of the equation goes to 0. So this gives you an opportunity to relate the virial, which is ri dot fi time averaged, equal to twice the kinetic energy, which is also taken in a time average. Now, if you calculate this ri dot fi, I mean using the standard gravitational force law, and then it will be simply like minus sum over I, sum over j, where I and j summed over are once again the different galaxies residing in the cluster, and its internal kinetic internal interaction, gravitational interaction, which is given by gmi mj by rij. And then, therefore, what you have is that you can now write this mi vi square average equal to this virial, which is sum over I, sum over j, g mi mj by rij. Now, if you assume a simple spherical distribution of the galaxies in the cluster, then this virial, which is the right-hand side, that turns out to be 3 by 5 g m total square by r total. And on the left-hand side, what you have that when you take in the sum over all the i's, which is all the galaxies over the cluster, then it will be m total v square average, which is the average dispersion velocities of the galaxies in the cluster, that can be written in terms of the total mass which is enclosed in the galaxy cluster. So with this observed velocity, which is roughly 10 to the power 15 centimeter square per second square, what you can do that you can actually calculate the total mass which is enclosed in the galaxy cluster, which Fritz Zwicky actually did. And what he found was actually that this is of the order of as you can see, that this is actually, so you calculate the total mass enclosed here. And whereas you, at the same time, you know that this Coma cluster is actually constituted of sun-like stars, which are of the order of 10 to the power 7 number. So what you see now, that there is a huge discrepancy between the total mass that you calculate using this virial theorem in the galaxy cluster versus the observed mass of the galaxy cluster. And this missing mass information, if you may say, he attributed to the presence of some non-luminous matter present in the galaxy cluster, and that's precisely what he called in the German language Dunkel Materie, in English, which means dark matter. So in a sense, Fritz Zwicky was the father figure of coining this term dark matter and finding the first evidence of it in this kind of astrophysical systems. However, there is one point to say here, that his paper was actually written in German, and it didn't reach many people. So therefore, actually around 1970s, it was Vera Rubin, who was, as a graduate student, studying the angular motion of the galaxies by galactic rotation. And once again, what she did was a simple calculation, which we can all understand. So basically, you can understand that the motion of the stars in the galaxies can be simply understood by this classical equation like mv square by r equal to gmm by r square. Correct? Now, where this small m is the mass of the stars in the galaxy, which is rotating in the galaxy. And then this capital MR is a mass which actually this smaller stars, this star actually is encircling about within the galaxy. So this is the galactic mass, MR, and this V is the velocity with which the star is moving in the galaxy, okay? And R is basically the radial distance from the center of the galaxy, okay? So this equation is something that we all understand. Now, it is also quite easy to understand that when you are within the visible galaxy cluster, then you can actually scale this MR to be something like, once again, an uniform distribution like 4/3 pi r cube into rho, where rho is the density that you can attribute of the stars within this galaxy. And then you can find out that this VR, the velocity, will be actually proportional to R. That basically means that when you are going outward the galaxy, within the visible galaxy, then the radial velocity will keep on increasing as you go out. Okay. Now, what happens when you go out beyond the visible galaxy cluster? Because then you can assume this MR is actually a constant capital M. All right. And then your VR should actually fall off, right? 1 by square root of R. That is once again a trivial way that you can actually see. So therefore, what you expect is shown in this picture by this orange dotted line, and this is how what is actually expected. So your radial velocity actually increases within the visible galaxy, and then it actually should fall off as you go outside the visible galaxy. But what you actually observe is actually this green dotted line, green dotted points, and the line that actually joins it. So you see that instead of falling off, actually this radial velocity actually almost remains constant, or actually it goes to increase a little more. So then this was also a very striking observation, which led Vera Rubin to conclude that there must be a dark matter halo present in this actually galaxies, and that actually changes your rotational velocities of the galaxies instead of falling off to give you a rough constant. And this is once again a very important observation, which actually led people to think about the possibility of dark matter being present in the galaxies and galaxy cluster. So I was seeing that there was a raised hand. So is there an immediate question?
No, the questions will be asked by Saurabh, and maybe there is a technical problem. You need not worry about the raised hands.
Oh, all right. So the slides are visible, and I am audible.
Yes, okay. You are audible. The slides are visible.
Okay. Okay. So let me carry on then.
Yes, please.
Okay. All right. All right. Very good. So let us talk about the third observation, which we made actually recently. It was around 2006 that Chandra X-ray Observatory actually could see the merger or collision of two galaxy clusters. The smaller one is also actually called the Bullet cluster. So we usually call it by that name, that this observation in Bullet cluster. And this actually shows once again something very striking. And this is shown in the picture. So in the middle, by this pink color, you see that this is representing the luminous matter which is actually present in this collision, and this is basically the hot gas which was actually seen in the X-ray. And you see that this when the collision occurs, they are actually strained a bit, like in this direction, and so this is what was observed. Now, there is another thing that you see in this picture, which are two blue blobs, actually, which are sitting on the two sides of this middle pink region, right? So these are the two blue blobs. Now, these blue blobs were not seen by the telescopic eye, but this was inferred from what we call the gravitational lensing. Now, what is gravitational lensing? We many of us know that Einstein's theory of relativity has taught us one very important lesson, and that is basically the fact that gravity actually bends the space-time. space-time. So when light traverses, actually it takes that distorted space-time trajectory. And when you are trying to see an object which is sitting far away from you, and there are some luminous matter which is bending the space-time, then actually you create a set of images of that object. And this is what is called the gravitational lensing. Now, this bending of space-time is not only created by the luminous object, luminous matter which is present between you and what you are trying to observe, but also by the non-luminous matter which is present here. So that will actually distort whatever the images that you form, correct? So therefore, by that virtue, you can actually conclude if there is some non-luminous matter which is present in any observation. So this is precisely what these guys did in case of this merger of the galaxy cluster. And they could infer that when this merger occurred, when this collision occurred, there is a big chunk of mass present in the galaxy clusters, which actually passed each other almost in a non-interacting way and actually created these blue blobs that you see around. So this was once again attributed to the presence of some non-luminous collisionless dark matter. So these are three very important observations coming from astrophysics. And I will just briefly talk about some observations from cosmology now. And this observation comes from what is called the cosmic microwave background radiation, which is in simple called CMER. And that actually yields you a measurement of the constituent of the universe at the current. And what is CMER? CMER is basically a radiation which left 13.8 billion years before, when the first neutral object, which is the hydrogen atom, was actually formed. And let me briefly tell you what happened, that after the Big Bang, everything was there. I mean, like the photon, but the universe was actually opaque because the photon couldn't move freely, because it could find the charged particles like electrons and protons as it moves by. Okay, so therefore it was the photon couldn't have a free streaming length. But after the electrons and protons form this neutral hydrogen, the photons started moving freely, and then that radiation is what we call the CMER radiation. Now, this was the discovery of Penzias and Wilson around 1970s, and they studied, and we see that it's mostly a uniform black body radiation, but the point is there are some tiny fluctuations in it, and these tiny fluctuations actually give you something very, very robust. And this is something which I'm going to just now point out, that this this figure that I just showed you is actually when you put these fluctuations in terms of the multiple moments, but never worry about those details. But let us focus on what kind of inference that it actually draws. And the inference that it draws is something amazing. It says that when you fit these anisotropies with the standard model of cosmology, which is also sometimes called lambda CDM model, then you find that the ordinary matter only constitutes 4.9% of the energy budget of the universe. Dark matter constitutes something close to 26.8% of it. And the rest of it, which is roughly 70%, is constituted of something even more abstract and amazing, which we do not have almost any idea about what that is, and that is what is called the dark energy. Okay, so this is what the information that we actually gathered from this CMER measurements. And there are experiments like WMAP and Planck who actually have confirmed this observation or conclusion again and again. So this is something that we have to take very seriously. And this gives you one very important inference, which is about how much dark matter is actually present in the universe. Okay, and this is often recast in terms of this omega h square, where omega is called the cosmological energy density, and small h that you see there is actually the Hubble expansion rate in the units of 100 km per second per megaparsec, and omega h square is the order of 0.12 roughly, say, for example. And this is a very important number that all the dark matter enthusiasts abide by, and this is what is called the relic density of the dark matter. And it was actually the works by Professor P.J. Peebles which led us to this kind of understanding, and he was awarded with a Nobel Prize in 2019. So with this, I'm going to finish this section of the evidences that we gather for from different astrophysical cosmological experiments for the existence of dark matter in the universe. Now, once we know that this dark matter exists, then the question comes that what can be a dark matter? What is a dark matter? Now, there are some, you have to find some suitable candidates for dark matter for sure. And the question is, what suits a good dark matter candidate? Now, it turns out that if you have to satisfy all the observations that I just talked about, you can imagine them to be constituted of some fundamental particles, but they must be having some broad characteristics on their own. What are those characteristics? Now, the first thing is quite obvious, that the dark matter has to be dark. That means it cannot have electromagnetic interaction. You see me, I see you, you can see the slides, because everything is consisted of electrons, correct? And therefore, there are electromagnetic interactions by virtue of which we can see all the things. But so therefore, this is very important that the dark matter should not have any electromagnetic interaction, or in a sense, you can say that it has to be electromagnetic charge neutral so that it can be a dark. The second point is it has to be stable, because we have passed almost like 14 billion years of the history of the universe, and we still see dark matter around. So it cannot have escaped and decayed into some other stuff. So it must be a stable particle. And the stability of a particle is importantly assigned to the symmetry under which this particle actually transforms. For example, electron is a stable lepton because it's the lightest particle having a lepton number symmetry. So similarly, therefore, when we make a dark matter model, this is the second important credential that we assign, that the stability of the dark matter has to come from some transformation of that particle under some symmetry group. So this is some technical aspect which will come later. And of course, it has to be massive, because all the evidences that we have gathered are actually coming from some gravitational effect. Now, there are actually three very important categories, or rather three important type of particles which can actually satisfy all these credentials that we have accumulated for the dark matter. One is called weakly interacting massive particle, or WIM. We are going to mostly focus on this part. There is also something called strongly interacting massive particle, or SIMP. And lastly, there is something called feebly interacting massive particle, or FIM. They are actually classified based on the interaction of these dark matter particles with a visible sector, with the particles that we see around. And this is actually classified into two major categories, like the way that they are produced in the early universe. And the first two categories, like WIMP and SIMP, fall into something called thermal freeze out. And the last one, like the FIMP, actually falls into this non-thermal freezing category. Okay, so we are going to talk about briefly about the thermal freeze out and the WIMP category in our next few slides. And although we have attributed these credentials for dark matter, there are many things that we do not know about them. For example, when we talk about fundamental particles, there is one immediate thing that comes into the picture, that what kind of particles they are, correct? I mean, they can have intrinsic spin of half units or 0 units or 1 unit. Like they can be scalar, they can be vector boson, they can be fermion, they can have even more complex spin, so that is unknown. They can be a single component or multi-component dark matter. That means that the dark sector can be constituted of a single type of particles, or there can be many different types of particles which constitute the dark sector. That is also unknown. Then the next important question is, what is the mass of this dark matter? Because we said that this has to be massive, but what is the mass of it? That is something that is unknown. What is the coupling with the visible sector? Because this different categories that I just pointed out is based on this interaction of the dark sector with the visible sector particle. So these are all unknowns that we have to actually leave so far, and then look for its properties or exploration in different experiments. That is what we are going to talk about in a moment. All right. So, but before trying to ideate or constructing a dark matter model, the first question is that in the known list of particles, which is in the standard model of particle physics, can we see any dark matter particle? Now, I have already said that for any particle which has to fit the bill for dark matter, has to be stable, has to have electromagnetic charge neutrality. These are two very important properties. Now, in the standard model of particle physics, of course, there are majorly 4 categories of particles that we see. One are called the leptons, one is called the quarks, one are called the gauge bosons, which are essentially the force carriers of strong electromagnetic and weak interactions. And the last category is what is called the Higgs boson, which is a scalar. So we have fermions, we have vector bosons, and we have a scalar. All these are there in the standard model. So if you look into the list of particles, so in this purple block, you see all these quarks are listed, like up, down, charm, strange, top, and bottom. Now this actually have strong interactions. They are also electromagnetically charged, so there is no questions of them to actually constitute the dark sector. What about leptons? Electron, muon, tau, they are actually electromagnetically charged, so there is no question about them. What about the gauge bosons? For example, gluon, that actually has a strong interaction. Like the Higgs bosons, say for example, if we start with, that is a charge neutral particle, but that actually decays. So then you actually go for the gluon, and the gluon has a strong interaction, and it can also cannot also form the dark sector, because dark matter cannot have a strong interaction in it. What about the Z boson? Z boson is actually a electroweak gauge boson, which is charge neutral, but it actually decays, so it cannot also fit the bill. Okay, and so what you are left with is actually this these three neutrinos essentially that you are left with, which could be potential dark matter candidates, because they are electromagnetic charge neutral first of all, and they only have weak interactions, and they also do not decay. And I missed the part of the photon. That photon itself is electromagnetic charge neutral, but it actually interacts with only particles which has electromagnetic charge, so photon is out of question. So the neutrinos could only possibly form the dark sector, but there are two troubles associated with it. Number one, that it has a very tiny Rayleigh density. The second is because they have a mass which is of the order of electron volt, so they have a large free streaming length, and that goes against the virtue that dark matter should actually help us to form the structures in the universe. So it goes against the structure formation. So to summarize this slide, essentially we say that in the known list of standard model particles, there cannot be any dark matter that we are looking forward. So what is the possibility? We have to build some models. We have to extend the standard model to actually have the dark matter for the universe. Now, the simplest way to do it is to actually sketch the dark matter standard model interaction, because that is the one which actually is the most crucial one that actually gives you the gives you this inference that how you actually calculate the Rayleigh density. As I said, that the classification of how dark matter particles can be, like film, SIMP or film, actually boils down to the fact that how this dark matter interacts with the visible sector particles. So the simplest possibility is to assume that there is a 2-2 interaction, like there are two dark matter particles interacting with two standard model particles. This is the simplest possibility that you can think of. And when you, I will come to the details of this picture, this cartoon picture that I'm drawing here. And this basically shows that I do not know what is sitting in the blob, what specifically guides you to write this interaction. But essentially, this kind of interaction is something we have to write. Now, mathematically, when what you write is a Lagrangian density involving this interaction term between the dark sector and the standard model particles. And this can be written in terms of two operators, one operator which consists of dark fields, and one operator which I called OSN that consists of the standard model fields. Now, when you construct this operator, the interaction between the dark matter and standard model, there is another thing that comes into the picture, is actually what is the mass dimension of these operators. If the mass dimension is larger than the mass dimension 4, then this is called effective interaction. And therefore, in order to make the whole interaction of mass dimension 4, you have to actually divide it by some new physics scale, lambda to the power n-4, whatever the dimension that you have for the operators ODM and OSM. There is another point that you have to borrow in mind in order to build this kind of dark matter model, that the dark operator, which you call ODM, has to respect the dark symmetry by virtue of which you make the dark matter stable. On the other hand, the OSM has to be stabilized under the standard model gauge symmetry, which we all know to exist. Okay, so these are the basic building blocks of building a model for the dark matter. Now, I will give you a quick glimpse of the simplest possible dark matter model that you can build, and that is actually at the renormalizable level, where you assume that this total operator ODM multiplied with OSM has a mass dimension of 4. Then you can divide it into half and half, like you assign mass dimension 2 to ODM, mass dimension 2 to OSM. Okay, and so therefore in the mass dimension 2, in the standard model, there are only two standard model gauge invariant terms that you write. One is H dagger H involving the Higgs field, and the other is B mu nu, which is the field strength tensor with U1 hypercharged field that you actually have. Now, if you focus on the H dagger H term, this actually gives you one simplest possibility of writing a ODM OSM dark matter standard model interaction, where you stitch H dagger H to a scalar which you call phi, and you write it like H dagger H phi square. Now, in the scalars, all the fields have mass dimension 1, so therefore this is a renormalization term, a renormalizable term, and therefore you can assign a dimensionless constant above, in front of it, and try to find out the correct relic density allowed parameter space for a set of parameters like mass of the dark matter and whatever the couplings that you assign to it. And this is what is called the Higgs portal interaction dark matter. And this is the simplest dark matter model that one can actually think of. There is another point which I mentioned before, and I would like to reiterate now, that phi has to have a dark symmetry, correct? So otherwise, I could also write a term like H dagger H phi. In that case, phi will decay to the standard model particle, and then it will violate the stability criteria. So what you further impose is that there is a Z2 symmetry under which phi goes to minus phi. And so therefore, the only terms that is allowed with this dark field is of the order of phi square. So that only renormalizable dark matter standard model interaction that you can write is H dagger H phi square. So this is a valid dark matter model which people have studied. Now, the important point is that once you are able to write this dark matter standard model interaction, then this interaction itself can actually detect you how to search for this dark matter in different experiments. Like now, if you focus on this cartoon once more, and if you look vertically upward, this interaction can give you a possibility of dark matter scattering off your detector, like dark matter interaction with the visible sector, but where the dark matter scatters off the a detector nuclei, and that is what is called the direct detection. So I will talk about them. Then there is also a possibility that you smash visible sector particles and annihilate into the dark sector particles, and that is what is called the collider search of dark matter. And the third possibility is the indirect detection, that at present in the galactic centers, etc., your dark matter can annihilate and produce some standard model particles which you can observe and infer about the presence of dark matter. So these are the three different search strategies which are also correlated with this dark matter standard model interaction that you can cook up. Okay, so let's proceed. Okay, so let's proceed. So I told you that I will briefly talk about the Wink freeze out of thermal freeze out of the weakly interacting massive particle. And let me give you the basic philosophy of it, that what we assume is that in this particular case, that the dark matter actually was in equilibrium with the hot soup of thermal standard model particles via this 2-to-2 interaction that I just give you a quick cartoon model. So this was in interaction, it was in equilibrium because the rate of interaction was much dominates over the rate of expansion, which is actually represented by the Hubble expansion rate. So when the gamma is much less than h, where gamma represents the rate of interaction of the dark sector with the visible sector particle, when it is much more than the rate of expansion, then it is actually in equilibrium with the thermal path. Now, when the universe expands and cools down, the rate of interaction basically at some point of time falls below the rate of expansion. And that is when the dark matter cannot keep up with the equilibrium any further, and it actually freezes out from equilibrium. And this is what is actually mathematically captured by this so-called Boltzmann equation. And never worry about the details, but let me briefly talk about what this actually represents. That you see that on the left-hand side, you have a dy dx, where y is called the yield of the dark matter, and x is a variable which is represented in terms of dark matter mass by the temperature. And on the right hand side, you see that there is this y square minus y equilibrium square. And what you assume that at a very high temperature, y was actually y equilibrium. And then the question is, how does this y actually goes as the universe expands? and it cools down. And there is an important prefactor to this, and that is actually the thermal average of the annihilation cross-section of dark matter. And that is basically the rate of interaction the dark matter has with the standard model particles. So you can assume in a short that this Boltzmann equation, which governs the freeze out of the dark matter or determines that when the dark matter will go out of equilibrium and give you the correct relic density of the universe, is governed by the rate of interaction of the dark matter with the visible sector particle, which is represented by this thermal average of this annihilation cross section. Now, if you solve this equation very roughly, once again, depending on whatever dark matter model that you choose, you see that this Y equilibrium distribution is this Maxwell-Boltzmann distribution. It is roughly e to the power minus x. So in the Y versus x plane, this is this falling distribution. So initially, the dark matter was in equilibrium. Now, at certain point of time, this, as you see that these three different lines, which has three different rate of interaction, three different gamma, that actually freezes out and give you a constant in this Y versus X plane. So basically it says that in the co-moving volume, the dark matter density becomes constant, and this is what attributes to the relic density that we talked about. Now, what determines this freeze out point? That is basically the rate of interaction, and you have to judiciously balance it so that you actually get the correct relic density. Now, it turns out that for this kind of 2-to-2 interaction, to give you the correct relic density, the rate of interaction that the dark matter requires to have with the standard model bath has to be of the order of weak interaction cross section, which is roughly, you can assume, of the order of 10 to the power minus 10 GeV to the power minus 2. Okay, so this what gives you the rough idea of what WIMPs do or how does it freezes out in the early universe. Now with this, I come to the last part of my talk. Now I will talk about the search strategies, which I just briefly discussed. Let's start with the dark matter direct search. Now you imagine that cartoon graph, that dark matter standard model 2-to-2 interaction actually allows you to have a dark matter scattering of your detector nuclei if you can actually cook up an experiment of that sort. So basically the idea is that we are all moving in the halo of dark matter. Our galaxy is immersed in a dark matter halo, which has a distribution, and then there is an elastic scattering of the dark matter that can actually occur with the detector nuclei given by that dark matter standard model interaction strength. And however, you cannot see the dark matter, but what you can see is the nuclear recoil, which actually comes out of the energy momentum conservation out of this collision. So this is a very brief cartoon which I have. So this is your detector, and then your dark matter comes, hits your detector, and the velocity is of the order of 200 kilometers per second. So it's a non-relativistic scattering. So there is no way that you can actually have an inelastic scattering. You have to rely on elastic scattering event, that you have a dark matter elastic scattering, and then there is a nuclear recoil, and that is something that is measurable in the experiments, and that is what you measure in this mathematical formula. And you can imagine there are some inputs which goes into this formulae, like the velocity of the dark matter, the velocity distribution of it. Then there is this dark matter density, which is rho 0, mass of the dark matter, mass of the nuclei, so on and so forth. And then there is, you can also calculate this ER, which is very simple, the recoil energy, which is simply mu square V square by Mn into 1 minus cos theta. This is a very straightforward kinematics that anybody can do, where theta is the scattering angle. And so therefore, and here mu is basically the reduced mass, V is the velocity of the dark matter, Mn basically is the target nucleus mass, and so on and so forth. Now, this velocity distribution f of v that you see is actually an astrophysical input. Once again, this n-body simulations people have done, and they have attributed it to a Maxwell-Boltzmann distribution like exponential of minus v square by 2 sigma square. And you can assume that this limit of this integration on d cube p goes from a v minimum, you can call it from a v minimum, which is required to produce the threshold recoil rate, and the maximum limit is the escape velocity, which is roughly 600 kilometers per second. And the theoretical input essentially comes from this d sigma DER tar. That is the one that is actually calculated once you have that specific blob, this 2-to-2 interaction, whether you take it a simplest scalar dark matter model that I talked about, or more complex models, whatever that you like to do, that will give you this d sigma DER, which has different inputs. Let's not go into that, but you can imagine that at the quark level or at the fundamental particle level, you first calculate the cross section, then you actually fold it with the nucleon form factor, and then finally you have to have a nuclear model to actually find out the nucleus level interaction, and that's what people do. Now, let me give you a pictorial description of this. Is the recent most experiment which is going on. This is the liquid xenon experiment. So you have a xenon is the one which constitutes the main part of the detector. So the dark matter comes and hits it, and when it scatters off, then essentially it creates a nuclear recoil, which can trigger an electron, and which can go to the end cap and create another signal. So this is the way that this direct detection actually goes. So this is a standard technique. By the way, there is one last point that I would like to mention before going to the next slide, is that this technology of dark matter direct search was first ideated by one of the famous string theorists, which is whose name is perhaps known to everybody, who is Ed Witten, around 1985. So so now the question is, what is the result? What is the status of direct dark matter search? The point is, the result is still not very confirmed. We haven't yet confirmed the dark matter signal yet. And what it does, that this absence of a dark matter signal basically puts you some constraints on the dark matter nucleon cross section versus the dark matter mass plane. So this is precisely the figure that you actually see here. So you see a lot of lines. These lines basically means that they say, all right, I was looking for a dark matter signal, but I haven't been able to find it. So basically I predict that if there is no dark matter signal within the sensitivity with which I'm actually searching for, then this part of the dark matter nucleon cross section is actually completely forbidden. So basically they put a bound on the dark matter nucleon cross section versus dark matter mass plane. So these are all these lines that you actually see here. So as a particle theorist, what we usually do, that you come up with some dark matter model, whichever you think is interesting enough to search for dark matter. Then you find out the relic density allowed parameter space of it, and then you calculate the dark matter nucleon interaction cross section for that relic density allowed parameter space, plot it on top of this plane, which is WIMP nucleon cross section versus dark matter mass plane. Okay, and then you look for the recent most bound which has come from the dark matter direct search. For example, the xenon 1 ton has given a sensitivity close to 10 to the power minus 47 or 48 order, and then you basically say, well, all right, this part of the parameter space which resides below the current sensitivity of the direct search bound is the only allowed parameter space of the model, and you tell your experimentalist friends that please look into the dark matter in this region of parameter space for me. So this is what you do. And so there is another point before we leave this page, and that is actually about the neutrino flow, which you see in the orange dashed lines, which is plotted here on top of this, all these many different dark matter search results. And this basically tells you that when the search sensitivity goes down a little more, this dark matter nucleon interaction cross section reaches to a sensitivity where it matches to neutrino nucleon interaction strength. And that is what defines this neutrino flow. And this specifically means that if we do not discover dark matter in maybe in the next couple of years in the direct search, then we have to deal with a very important fact that we have to distinguish this dark matter signal from the neutrino flow, that is the neutrino background. So that is one area where people are also gearing up that how this can be distinguished and so on. There is one news of which I would like to point out, that very recently there was some excess which was observed in xenon 1 ton, but that was actually observed at a very low mass. And you see that because of this low sensitivity at the low dark matter mass of this detector, these bounds are actually going very mild on that low mass sector. So any observation over there, you have to take it with a bit of caution. So therefore people are excited about it, but we still do not claim, I think, that this is a discovery of dark matter. So this is all about the direct search that I had to tell. So basically the fact is that direct search is a search strategy for the dark matter, having a elastic scattering with the detector, and the search is still on, and people are doing many different experiments, including one that I just talked about, like xenon one-ton experiment, which is going on, and we are yet to confirm a dark matter signal, but the search is on. Now let me come to the next search strategy. What is my timeline? How am I doing with respect to time? How much time do I have?
Yes, you have time. It's 4:46. You have time.
Okay, all right. So, all right. So let's talk about.
We can take the questions. We have questions, and so you have time till 5.
So should I? Okay, all right. So roughly 10 minutes. I have to. I have the time to speak.
Yes.
Is it? Okay. Okay. All right.
Yes. No issues.
Very good. Very good. Thank you so much. Okay, so let us carry on with the other search strategies of dark matter, and let us talk about this collider search strategy. Now, you remember once again that two interaction that I just briefly talked about, that two dark matter interacting with two standard model. So there is one possibility that this, when you smash these visible particles or standard model particles, you can actually produce dark matter by virtue of that same interaction that I sketched. And so this is what is happening, so this is the arrow from left to right, which can give you or rather produce your dark matter at the colliders. And there is a recent collider experiment which is going on in CERN, Switzerland, which is called the Large Hadron Collider experiment, where you are smashing two protons at very high center of mass energy, almost at the velocity which is close to the velocity of light at very high energies, and you can create a bunch of standard model particles. But at the same time, if dark matter has an interaction with the visible sector particle like this, you can actually produce them in the collider also. Now here, I would like to just have a very small video for you. I mean, just to give you a feel of what the collider experiments do, particularly at LHC. So see.
Two protons approach each other. The protons have been accelerated to very high energy, practically the speed of light. Let's zoom in on one of the protons. It is composed of 3 quarks, 2 up quarks and 1 down quark, moving around very close to each other. The quarks are kept together by a number of gluons interacting with the quarks and also with the other gluons. The gluons give rise to the gluon field that keeps the constituents of the proton together. When the two colliding protons get very close and overlap, a gluon from one of the protons transforms into a quark and an antiquark. The antiquark interacts with a quark from the other proton. In interactions like this, a Z0 particle is sometimes produced. It decays almost immediately. The Z0 particle can decay in several ways. The decay into an electron and a positron is rather easy to detect in the Atlas detector and gives rise to an easily detected Z0 signature among the numerous particles produced.
All right. So basically, this in this one, actually, they talked about one specific particle production, which is Z boson, which I just give you, which I briefly talked about in my slide with the standard model particles. But you can produce anything and everything essentially. Now the point is, how do you produce dark matter? Once again, there are basically two major ways that you can produce the dark matter. First of all, if your dark sector has more particles than the dark matter itself, which you can have in many examples, like for example, people talk about supersymmetry, extra dimensional models, where there is a dark symmetry which stabilizes the lightest particle to be the dark matter, but there are heavier particles that can be produced copiously. Now, once those particles are produced, they can further decay into dark matter, emitting some leptons and jets, and that what gives you the first possibility, which is multi-lepton plus multi-jet signature. Then there is a second possibility that you have a very, simple dark sector, like the one that I talked about, like you have only a scalar singlet, which constitutes the dark sector. So then you have nothing to produce excepting for the pair of that dark matter itself when you collide two protons. So you produce two dark matters, and then you can actually irradiate from initial state, which are having both electromagnetic charge, weak charge, and the strong charge with the protons have. So they can actually radiate something called a photon, a jet, a W or a Z or anything. So this actually gives you what is called the mono-X signature. Okay, so this is but the point is mainly that the dark matter doesn't have any electromagnetic charge in it, so it doesn't interact with the detector, so it escapes the detector. For example, the movie that I showed was actually for the Atlas detector. So there is this Atlas and CMS detector. Also, there are Alice detectors and so on. But the point is, dark matter doesn't register in the detector because it doesn't have any electromagnetic charge. So what exactly it is going to give you? This is what is called the missing energy. So they are going to give you something called missing energy. Now, what is this missing energy or missing transverse energy? That we can understand very simply. Now, let's consider a collision, a very simple collision like AB going to C plus D plus C. And let's assume that D and E, these are the two dark matter particles. Now, we already know that in a 2-to-2 collision, there has to be at least two dark matter. And then let's assume that this C is actually one of the initial state radiations that I just talked about in this mono-X signature. Now, once you produce this pair of dark matters in this collision, let's see how do I actually identify this missing transverse energy or missing energy that characterizes the presence of dark matter produced in the collider. Okay, so let's choose this axis to be XYZ and let's assume that the collision occurs along the Z direction. So AB smashes, these are the two protons, for example, and produces your C, D, and E. Okay, now the missing transverse energy is associated with the dark matter, correct? So therefore, it is defined with respect to the X component of D momenta and E momentum added together squared, and Y component of the D momenta and E momenta, where D and E are the two dark matter particles that I'm producing in this experiment, added together and squared, okay, and taken a square root. So this is what is, so that is why this is called transverse, because the collision is occurring along the Z direction, but what we are measuring is the X component momenta of associated with the dark matters that are produced in this collision. Now, the next immediate question that you will ask, that these are not measurable because I do not know what is PXD and PXE and PYD and PYEs are, because these are dark matter. These are not detected in the detectors that we have in the collider. However, there is one important point, that because I assume that the collision is occurring in the Z direction, there will be a conservation of momenta, and along X direction and Y direction, this momentum will be identically zero. So PXC plus PXD plus PXE will be zero. So that basically tells you that PXD plus PXE will be minus PXC, and similarly PYC plus PYD plus PYE will have to be zero. So therefore PYD plus PYE is nothing but minus PYC. So basically that means that this dark matter transverse energy that you have defined above can now be written in terms of the transverse momentum of the visible particle that you actually produce. That's why we require a visible particle to be associated with the dark matter if we have to detect that kind of event. That's why this mono-X signature is something that is very important. So therefore, the missing transverse energy or missing energy associated with the dark matter is associated with the transverse visible energy of that event, and that is something which you can measure in the experiment. So LHC has also been measuring this kind of events, but once again, if you never worry about the details, these are missing energy distributions of some events gathered from CMS monojet search, mono V search, essentially monojet and mono V search. And this basically shows that the data that you have accumulated matches with the standard model background very well. So all these different colored histograms that you see are those kind of events where the standard model production mimics this kind of dark matter signal that you are actually producing in the collider searches. So for any experiments, if we have to bother about discovering a signal, we have to understand the background very well, and that actually needs a very sophisticated analysis and also huge statistics, which LHC is currently doing. So far, the data matches with the standard model background pretty well, and we have to wait for higher luminosity and higher statistics. Then the search strategies are also, enhancing much more. So no dark matter signal yet, but no worries. We are all working to find a signal. And lastly, I will talk about the indirect search of dark matter. So dark matter can also self-annihilate and produce some particle-antiparticle pair in the galactic center in the highly dense regions like the galactic center. And particularly this antiparticle production is important because in the universe, although from our quantum field theory, we know particle and antiparticles are equally probable, but the point is we only see particles and do not see much of antiparticles. So therefore, if we see some excess of antiparticles, that can be attributed to the annihilations of the dark matter in this kind of regions. So you can see, for example, so the idea is look up in the sky with ground-based telescopes, balloon-borne detectors, or some space-borne experiment, and you look for example, like positron excess, which is the antiparticle of electron, which was done by AMS, and you also by DAM, and they both quoted some excess of events in this regime, and also in terms of in the gamma rays, for example, Fermi-LAT, they pointed out some excess in those gamma ray events also, which can be attributed to dark matter signal. But the problem is that all this WIMP modeling that we do, that actually that is not good enough to actually satisfy all this excess. So you need to do some kind of more modeling, complicated modeling. So however, people are doing more rigorously those stuff, and people are trying to confirm if they can talk about more precisely about what kind of dark matter that can produce this kind of excess and so on. There are lots of works that is going on in this indirect search front as well. So now it's time that I summarize. So basically, I have talked a lot and basically tried to give you some idea of the evidences of dark matter that we have accumulated. And based on those evidences, we have identified some credentials which we should attribute to the dark matter particle. And based on that, we also have developed some search strategies of the dark matter in direct, indirect, and collider searches. And we are doing these experiments. And so far, we do not have a confirmed dark matter discovery, but I think it's not yet time. The coming years are going to be pretty engaging and interesting, and I think we are going to come up with some positive results very soon. So I will just flash one slide with my colleagues with whom we are actually engaged in different aspects of dark matter search at IITG. So you can look up in our web page and find this people, wonderful people working in all different sort of directions related to dark matter physics. So just to end, I remind myself of this word by Arthur Conan Doyle that once you eliminate the impossible, whatever I'm sorry, I cannot read the
whatever remains,
whatever remains, no matter how improbable, must be the truth. So basically the idea is, however you try and whatever that seems very improbable, but that has to be the truth. Once you remains, you eliminate all the impossible tasks. So this is what you have been doing. So you have a big parameter space of dark matter mass and couplings and models that you are looking for, and you keep eliminating one of them. And this is the history of particle physics, right? That is how the discovery of Higgs was there, and all these particles that we discovered was almost in the similar manner. So this is how it is going on. And so the hunt for this dark matter is on, and the question is, which dark horse wins the race? So thank you very much for your attention. Thank you.
Yes, thank you, Dr. Bhattacharya. It was such an informative talk. You talked about the evidences of dark matter as a second major ingredient of our universe's mass energy budget. You talked about the nature of dark matter as a candidate, as a candidate of weakly interactive mass particles. You spoke about the direct and indirect detection of dark matter. So I'm sure these are the things which I could, these are the headers which I could understand being a non-physics person. But I'm sure what inspired me, and I'm sure my students were also inspired by your passion for the subject, the passion with which you spoke. Uh, I'm sure my students out here must be inspired by it. Thank you so much. Thank you
Thank you.
for giving your time. So now is the question answer session, and we already have many questions when during the registration itself, and few are in the chat box. Now I would request from Dr. Shourabh Mitru from Department of Physics to conduct the question answer session. Over to you, Shourabh.
Yeah, hello. So, thank you very much, Dr. Subhaditya. And it was really, indeed, a very fascinating talk. And I hope we all enjoy that pretty much.
Yeah.
So,
I hope that I didn't speak too much, actually.
no,
So.
no, it's fine. It was within the time. So, yeah, we can now start the question answer session. So,
Surely.
first of all, I would like to mention that due to the time constraint, I might not able to take all the questions. But let me start with the questions, because we asked participants to put some of their questions in the registration box also, the registration form also. So I'll start from those. Okay, there are some questions like the theory of multiverse, multiple universe. So if you want to skip those, I mean, it's up to you.
Yeah, because I'm not an expert on those
Yeah, so
multiverse.
that's
Yeah, so
actually a scope of this talk also. So,
yeah.
there was some question about the works of Vera Rubin, but I think you have already mentioned in your talk. So I'm going to skip that also. Okay. So is there any possibility of primordial black holes being a candidate of dark matter?
Yeah, that's a very good question, and the answer is yes. So anything which actually spreads in the galaxy and doesn't have very heavy mass like the primordial black holes are, so they are actually a potential candidate for dark matter. That is absolutely correct. So there are lots of works which are actually going on, and even on the search strategies, actually people are thinking that how their signatures in collider or in direct search can be. So primordial black holes, yes. Actually, basically, because what we require, you see, there's this density perturbation like delta rho by rho that we require, right? And in the early universe, it is pretty easy to produce these primordial black holes quite easily. And so therefore, it is true that they can be a good dark matter candidate. That is absolutely correct.
Okay. So there is one question like, is there any way in which we can use, we can actually detect dark matter which can achieve the speed of light? And how did the scientist how can the scientist discover such things?
Yeah, so see, I mean, that very idea is that, I mean, there are three regimes, I mean, which I didn't talk about. I mean, you can have hot, warm, and cold dark matters. So the hot dark matters are like those neutrinos, which I talked about. The neutrinos are those invisible particles which moves with a velocity close to light. I mean, because whenever you have particle masses which are very, 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 very light, they can achieve velocities as much as they want. I mean, very close to light. Now the point is, there is one thing which this dark matter should also do, which is to help in help in gathering all the other visible matter to form these structures. And now it turns out that the potential that you can only construct using the visible interaction is not good enough. So that's one of the reasons that you also require this dark matter to be there. And the point is, this very idea that dark matter is having a very long free streaming length, like the neutrinos, I mean, they are relativistic guys, then it actually goes away against the structure formation, because it will oppose the whole process of bringing things together and forming structures. So that is one of the reasons that it is not taken very one of the things which goes against the idea of very light dark matter which moves with the speed of light.
Yeah, sure. So the next question, are there any alternative theories that that could explain the rotational curve of galaxies?
Yeah. So that is also a very important point. I mean, see, I mean, there are this modified gravity people. I mean, instead of writing your Einstein equation with just the Ricci scalar, you write it in terms of some FR where you scale it like r to the power n, and then you fit that n from the observation of this rotation curves. That is something that people have been doing. I mean, they do it actually. So to answer that, modified gravity is something which people have looked into to actually satisfy this rotation curves, but that actually miserably fails to describe other observations, like for example that in bullet clusters. So therefore, yeah, that's how it is.
Okay. The very similar questions actually asked by one of our young faculty here. So he also asked that can some of the dark matter observation be explained by the modified gravity, for example, some higher curvature theory like Gauss-Bonnet or the Lovelock models, even the
Yeah.
FR ones. So
Yeah, so I'm not a great expert of those specific models that you mentioned, but the answer is yes. You can study the rotation curves and fit the observation, like the rotational velocities of the galaxies going flat beyond the visible part of the galaxy very well with those FR. But many a times I have also seen. Once again, I have not worked explicitly on those areas, but many people do it. Say, well, all right, I don't like the Einstein's theory of gravity. I have modified gravity with some FR in it, where I do it like r to the power n and fit my n into it. And then they said, well, this doesn't satisfy all the observations. So let me do this. Plus, let me also put in some dark matter into it, and then satisfy the other observations. So this is the way that people also try to do it, which is like mix and match of both these things. So those efforts are also.
okay, yeah, sure. Okay, so someone asked about if so this is actually not related, but still, if you want to take that, if the universe is expanding, does the distance between Earth and Sun is also increasing, and also is there any dark matter in the solar system?
Well, actually, see, the dark matter distribution is actually sketched in terms of you see, I mean, this rho r, which is actually some rho 0 by 1 plus r by a whole to the power gamma, something like that. I mean, you take the distribution in a large scale. So in principle, of course, I mean, we are all passing through the halo of dark matter. I mean, that's how this, based on which this direct such experiments are sketched, right? That you have a wind velocity distribution. There is a wind velocity distribution in which you are moving, and then you place your detector, and then this dark matter comes and hits your detector and scatters off. So therefore, of course, there is a distribution. The velocity of dark matter with which it comes and hits your detector is very, very tiny, of the order of 200 kilometers per second or something. But yeah, I mean, about this expansion and the increasing distance between Sun and Earth, I'm
Yeah.
not quite sure actually. So I do not think that is the case. I mean, once
This
again,
is
yeah,
gravitationally bound system already there.
correct.
So okay, so okay, so there are a few more questions from the registration form also, but I think I should move to the question in the chat box. So
Okay.
okay, so someone asked about could dark matter be antimatter? So
Well, it can in principle be, because if you have a fermionic dark matter, so the point is the distinction between matter and antimatter very much comes from its electromagnetic charges, like electron and positron. How do you distinguish? You distinguish basically by the fact that the electron has electromagnetic charge of -1 unit, whereas the positron has a +1 unit, like this, right? So therefore, it's very well there. So if you have a fermionic dark matter, the chi bar, which is the conjugate particle, that will be the dark matter, but that antimatter and the matter together forms the dark matter, because everything is dark, and those are indistinguishable essentially.
okay.
Yeah. So
So
it's very much there. Yeah,
very much.
absolutely, it's very much
So,
there.
and okay, this one is also very interesting. Someone asked about could dark matter be made of more than one particular particles?
Yeah, this See, I mean, this is important because see, I mean, when we talk about our visible sector of the universe, we talk about electrons, we talk about leptons, we talk about quarks, we talk about gauge bosons, we talk about Higgs. So many different particles to attribute to weak interaction, electromagnetic interaction, strong interaction, which the visible sector consists of. Now, when it comes to the dark sector, because of our absence of knowledge, we usually say, well, let's assume there is one kind of a particle like a scalar singlet, which constitutes a whole dark sector. Now, as my friend here is suggesting me, that's actually a simplification to some extent, because we have no other ways of detecting the interaction between the dark sector particles, excepting for this observation of bullet cluster, which actually restricts your dark matter interaction less than, suppose, 1 centimeter square per gram or something like that. Uh, there are not many observations which tells us that what kind of particles actually constitute. So you can actually very well do a modeling where you assume that there are more than one dark matter, one scalar, one fermion, one vector boson, as you go on. So, and then you attribute the relic density appropriately to each of them and find out their potential in direct hand collider such. So that is a very much possibility.
Yeah. Okay, so but we are really running out of time. So one last question, I think, but there are so many questions anyway. So I think this would be very beneficial for our undergraduate students also. So which institutes in India are currently working on the experimental part of detection of dark matter?
Yeah,
I
this
think
is a very important question.
very
See, I mean,
important question.
Shaha Institute of Nuclear Physics, they have an experimental group in direct dark matter search that I know of. And then, you know, Saurabh, I mean, this is a very unfortunate story that we should not go in, but I should spell it out at this moment, that, when we were graduates, I mean, finishing our PhD, at that time, you remember that there was this experiment called INO, Indian Neutrino Observatory.
That was
Right.
sad story.
But so when I was finishing my PhD and going for different places to go my talks, everybody used to ask, oh, that's a very exciting news that you guys are going to have a detector very soon, and your own observations for, and there was a proposal of DINO that in the same laboratory, you also will have a dark matter detection, because it's very similar, as I just pointed out. So, but the unfortunate part is that never happened. So after that, I mean, almost like 10 years have passed, and I have all my hairs and beard are getting white, but that experiment is still not a reality. So there are a group of people in IIT Bombay and TIFR who are also associated to this DINO and all these things. But this is still going on at, I mean, I do not know what exactly the status is recently, but I haven't heard that this experiment has started or given any data. So that's.
Yeah, I remember some people from our institute, they actually got job.
Well, I mean, the job is a very good thing. I mean, everybody should get job, but at the same time, we should also have some data.
Okay, I think that will be all for the first session. So please, thank you again so much, Subodha. So I'll just hand over to us.
Yes, thank you, Saurabh. Thank you, Dr. Bhattacharya. It was a very fruitful interaction, and due to a paucity of time, we could not answer all. But students, you can contact your own Saurabh sir if you have any questions, and he would definitely try to communicate with Dr. Bhattacharya and answer all your queries.
Definitely.
Okay, so moving on to our next talk.
Okay, thank you very much.
Yes, thank you, Dr. Bhattacharya. থাকুন একটু প্লিজ, আমাদের নেক্সট স্পিকার এসে গেছেন, যদি একটু থাকতে পারেন।
Sudipta is an expert in real sense, so I'm also waiting to hear from him. So yes, let's all welcome Sudipta. Yeah.
Yes. So our next speaker will speak on Hawking and his universe. And to introduce our next speaker, I would now request Dr. Ronjit Maiti, head of the Department of Physics, to speak a few words and introduce our speaker. Over to you, sir, Dr. Ronjit Maiti.
Thank you, madam. Dr. Sudipta Sarkar did BSc and MSc from University of Calcutta. He got his PhD degree from IUCA, Pune. He was a postdoctoral fellow in University of Maryland, USA, and IMSC, Chennai. After that, he joined IIT Gandhinagar, and currently he is an associate professor there. He mainly works in the field of gravitation and black hole physics. He is an active researcher in his field and has published more than 35 papers in various international journals. In my opinion, he is among the best to talk about Hawking and his universe. So, without further ado, I welcome Dr. Sudipta Sarkar, our final speaker of today's program, to deliver his lecture on this topic.
Thank you. Thanks a lot. So let me first share my seminar slides. Give me a second. Is it visible fully?
Yes, not full length, but
Let me just again try. This should be okay.
yeah, now it's visible.
Okay. Okay. So may I start?
Yes, please.
Oh, okay. Thanks a lot. Thanks a lot for the introduction. So let me first thank the organizer for giving me this opportunity to present this talk. And first of all, Subhaditya has set a very high standard. It's not easy to even go close to his standard of his clarity, of his lectures. We all know how good teacher he is. Okay. So I'll try my best nevertheless. Okay. So first of all, I was actually in a little bit of dilemma what to talk about. Okay, when I was discussing with the organizer, initially I was thinking of talking about works related to recent black hole observation, shadow, and things like that. But then I realized that it is not a bad idea to discuss Stephen Hawking uh, and his theories. First of all, there is a huge interest on his life, on his research work, and it is also a very good time to talk about his extraordinary contribution for the understanding of the gravitational physics and black hole physics and cosmology also. Because we are living on a time where we have real data by which we can actually distinguish between general relativity and any other theories. In fact, now we have the observational ability to even distinguish whether this is a curved black hole or it is not a curved black hole. We are actually very close to that observational power. So this is probably the right time, also a good topic, and therefore I decided to talk about Hawking and his universe. So before I begin the lecture, let me say something about the structure of the talk. First of all, the life of Hawking is very well known through popular media, through books, movies, cinemas, and whatnot. So therefore, I am not going to talk about anything about his personal life and also not much about his life as per se. What I'm going to talk about is mostly his scientific work. I'm going to talk about what is his contribution to physics and why physicists, particularly theoretical physicists, consider him one of the greatest physicists of all time, maybe second after Einstein. Okay, at least in the next 100 years. Why his contributions are so important in the understanding of the fundamental laws of nature. So this is the premise of the talk. Let me start. So if you look at Hawking, so there are some very interesting coincidences. Okay, of course, this numerology has no scientific basis, but this is interesting. Just for fun, I am putting this thing. So Hawking is born on 8th January, which is the day Galileo Galilei passed away, of course, 400 years ago. And he died on 14 March, which is also the birthday of Einstein. It is also interesting to know that Einstein lived exactly for 76 years and Hawking also lived exactly for 76 years. Okay, so there is this amazing coincidence when you look for Hawking, look for anything about his life information and you see this information. So there are these three giants, okay, Galileo Galilei, Einstein, and of course, Hawking. I will talk about Newton immediately after some time, okay? And if you look at the writings of these people, Galileo Galilei, Albert Einstein, and as well as Hawking, you will see that they have always a fascination towards what is the thinking of God. Of course, by God, they actually never meant the usual God in religion. They meant something bigger. Okay. And they all have quotations in their writing about this concept of God. For example, Galileo's relationship with God, particularly the God of Christianity, is very well known. And he has written sometimes that I do not feel obliged to believe that the same God which has endowed us with the senses, reason, intellect, has intended to us to forego their use and by some other means give us knowledge by which we can attain by them. And of course, you understand the context of this quotation. He was fighting against the authority of the church and trying to put forward the case for science. Similarly, there is a very interesting quotation by Albert Einstein, which is used and misused in many times, where Einstein said God does not play dice with the universe in the context of the quantum probabilities. Then, of course, there's a very famous quotation by Stephen Hawking, which is in some sense a reply to the Einstein's quotation, which says, not only God plays dice, but he sometimes throws them in such a way that you cannot be seen, of course. So you see that all these three great men, okay, they were interested in big questions. Big questions which explain the origin of the universe and also the fate of the universe. These questions are not easy to understand. They are extremely difficult to understand. And sometimes finding the answer to this question is a lifelong quest. Hawking life is a testimony of that quest, which reflects that humanity's ultimate desire to know about the origin of everything. Okay? So let's go ahead and see. So to understand Hawking, we have to start with Newton. And we all know about Isaac Newton. Why Isaac Newton is very famous? For many, many reasons. His contribution to mathematics, physics, various branches of physics, starting from optics to mathematical physics to gravity, is very well known. Of course, the mechanics. And we all know about the Newton's theory of gravitation. What does Newton's theory of gravitation says? Very simply, this is even class 3 probably nowadays people know. If you have two masses, m and capital M, and they are separated by a distance d, then of course the force is F equal to G into mm by d square, where G is what is known as the Newton's constant. So what does Newton's gravitation, apart from the mathematics, what it simply means is that it's a universal attractive force which acts instantaneously. Between 2 points, the gravitational force is a universal. It does not depend on the nature of the object. It doesn't depend on the color, doesn't depend on the shape. It is always there, function of the mass of the object and the distance, and also it acts instantaneously. There is no mention of anything like time in the Newton's equations of gravitational force. And this is what the famous story that apple falling on the Newton's head. So I used to believe that story is not true, but recently I've read some very interesting writing that this could be actually a real story. Okay, but anyway, that's a separate issue. But immediately you see that there is a very interesting contradiction between Newton's theory of gravitation and the principle of special relativity. And everybody knows that principle of special relativity, which is probably nowadays also in the school syllabus, it says that you cannot move faster than the speed of light in vacuum. So there is a maximum speed limit in the universe. Nothing can move faster than the speed of light for whatever reason. Okay. So therefore, also gravity cannot move faster than the speed of light. So let's say the distance between sun and earth. Light takes about 8 minutes to come from sun to earth. Now suppose the sun is somehow vanished just now. Will the effect of gravity of sun will also vanish immediately at earth? That Newton's theory, the answer is yes, because gravitational force is instantaneous. Once suns vanish, at the same time gravity vanishes everywhere in the universe, presence of the sun. But then I will know that sun has vanished instantaneously. That means that information will flow to me faster than the speed of light. And this is prohibited by special relativity. So therefore, Newton's theory of gravity is in contradiction with the laws of special relativity. Very good. Okay. So light takes about 8 minutes to travel from sun and earth. What about gravity? And this is the question which Einstein set out to answer just after the discovery of the special relativity. And what it Took him about 10 years, and these are very, very interesting in history, how Einstein actually discovered the principle of general relativity. And this history is highly non-trivial because this is the first time where Einstein is also learning the language of geometry. But at the end of the day, in 1915, more than 100 years ago, he obtained the final form of the theory. And this theory is known as theory of general relativity. In some sense, very simply speaking, it is the relativistic theory of gravity. So it replaces Newton's theory of gravity by another theory of gravity, which is consistent with the principle of relativity. What is remarkable is that once you try to obtain a relativistic theory of gravity, it turns out that you have to consider a geometric picture. So this is not something Einstein desired. The mathematics, the physical argument led to him. It's clear that it directed him towards finding a geometric theory of gravity. So it turns out instead of the force picture, Einstein found a geometric picture where gravity is nothing but the property of the space-time surrounding the material object. So this is the picture which generally is being shown. This is a little bit misleading picture. There is no such shit between sun and earth or whatever. But the idea is basically is that just like the electromagnetic, like the charge changes something in surrounding and create what is called an electromagnetic field. Similarly, the presence of mass and energy changes the geometric property surrounding it and create what we call the curved space. And gravity turns out to be a manifestation of this curvature of space. Now, the consequence of general relativity is tremendous, that it shows that gravity affects the causal structure. Not only that, it can affect the flow of time and also the motion of light. This is something was not possible in Newton's theory of gravity. But general relativity showed that once you consider the relativistic theory of gravity, the flow of time, the causality between two events, all depends on the nature of gravitational force, okay, the gravitational field or the space-time surrounding it. And things are very, very, very non-trivial. So, to understand actually the universe of Stephen Hawking or the work of Stephen Hawking, we must start with this general relativity at 1915, where Albert Einstein revolutionized the entire basis of fundamental physics by giving us general relativity, which I just discussed. And as I told you, general relativity explains gravity as a consequence of the curvature of space-time. So how do I understand the curvature of space-time and all these concepts? Typically, it's a 2-semester course, but I'll just give you in 2 slides. Of course, things will not be clear, but let me try to give you an intuitive picture. So let's say suppose you have a plane of paper, okay? And on that plane of paper, you throw a ball, 2 balls. Depending on some initial condition, they can be either converging, or they can be either diverging, or they can be straight line, parallel to each other. Consider any of those cases. What we will see is that if they're converging, the distance between these 2 balls is decreasing. Similarly, if they're diverging, the distance between these 2 balls will diverge, increase. That's obvious. That's because you started with some initial condition that they are in the diverging trajectory initially. But you will never see that when they are diverging, suddenly they will stop diverging and again start converging. It will never happen on a plane of a paper. If you throw 2 balls on a plane of a paper, they will either continue to diverge or continue to converge and hit each other. But it will never happen that it will first diverging and then stop diverging and then again start converging. It never happens. In fact, geometrics, mathematicians can use this property to define what is called a plane. Okay, a flat plane can be defined by using this property that converging object will always converge till they hit, diverging object will always diverge. What is interesting is that if you take on a sphere, this is exactly what happens. Think of the lines which goes from North Pole to South Pole. Okay, the lines of latitude and longitude. Okay, note that the distance between these 2 lines first increases, goes to a maximum at the equator, and then slowly decreases and goes to the North Pole. And this is because we identify sphere as a space of what we call the positive curvature. This is just a definition. And you can also mentally see that the sphere is something like a curve, plane is something like a plane. Okay. Interestingly, exactly similar thing happens in the presence of gravitational field when two-point particle moves, and the diverging particle becomes converging because of the attraction of the gravitational force. Einstein used this. So in technical term, what happens is that the deviation, the distance between these two particles, first increases and then decreases. That means they have an acceleration. And Einstein interpreted this as due to the curvature of space-time. On a sphere, the curvature is a spatial curvature on the sphere, two-dimensional space. But for Einstein case, gravity is the curvature of the four-dimensional space, which you, of course, nobody can imagine. There is no need to imagine because there's a mathematics which we can guide it to you. What do you mean by the curvature of the fourth dimension or the fourth 3+1 four-dimensional universe? But nevertheless, it manifested as the physical effect is manifested as the what you call the gravitation. So if you can meet Newton and Einstein and you ask them same question, that why Earth moves around the sun, Newton's answer will be there is a force between Earth and sun called gravity which forces the Earth. And we all know this mathematics. There is a 1/r² force. We can write down the equation of the orbit and it will turn out the only course orbit is the ellipse, at least in 1/r potential. The Einstein's answer will be totally different. Einstein's answer will be the space-time around sun is no longer flat, and also the space is now curved, and therefore poor Earth is just following the curved path. But the question is, who is right? And it turns out there are many experimental and observational evidence which suggest Einstein's answer is actually the right answer. So, of course, I cannot discuss all the observational proof or the evidences in favor of Einstein's theory of gravity. Few you guys already know, at least in the popular level, that Einstein gave us the equations, how light interact with the gravity. And those equations suggest that when light comes near a massive object, it gets bends. And such bending of light is observed by observing the position of stars in the sky during the total solar eclipse. And it turns out the observation exactly matches with the Einstein's predictions. Similarly, there are very big clusters of galaxies. I'm sure Subhaditya has talked about this in the context of the dark matter. And you can study the bending of light in this cluster of studies, a cluster of galaxies, and which exactly matches the GR result. Okay. In fact, this is one of the reasons why people require an dark matter. Okay. So what is interesting is that all this experimental and observational results cannot be explained by Newton's theory. And therefore, they are evidences in favor of Albert Einstein's theory of gravity. So Einstein wanted an equation. Okay. Of course, you know, in physics, it's okay to give qualitative interpretation, but at the end of the day, you have to calculate. You have to give predictions, mathematical prediction, which can be checked in the experiment. So you need an equation. What is the equation? Gravity is the curvature of space-time. Why gravity? Because there is a matter. So you need an equation which will relate matter with the geometric quantity of the space-time. And this is what is called the famous Einstein's equation. I don't want to describe the Einstein's equation. They're quite complicated. But nevertheless, I just want to flash them because they look beautiful. And what this equation tells us, that it's information, the one side of the equation which has this strange symbol like r mu nu, half r g mu nu, okay? They describe the geometry. The other side is T mu nu, which many of you may know, the energy momentum tensor, which describe the matter and energy. And this equality sign is the connection between geometry and matter. So this is one of the greatest achievement of human mind, that one side is mathematics, pure mathematics of the geometry. The other side is physics. And in one equation, Einstein, related the two worlds, okay, through the Einstein's equation. So if you solve this equation, you get the solution of the Einstein's equation is the space-time geometry around the object, and that will give you what is the gravitational field outside an object. Good. So Einstein's equations are complicated. It is not easy to solve Einstein's equation. Even today, almost more than 100 years after the discovery of Einstein's equation, solving them using computer is a non-trivial job. In fact, there is a completely different field called numerical relativity, where people are devoted in solving Einstein's equation on computer. That is because mathematically these equations are nonlinear partial differential equation. Okay, hyperbolic nonlinear partial differential equation. And the general mathematical theory in understanding the properties of the solution of this equation is not yet there. Okay, so therefore it's not easy to solve them. Okay, but you can make very simple assumption. For example, and this is what physicists always do, you try to solve it for spherical system. Okay, so you close your eyes, you said, look, I don't want to do a very complicated thing. I will assume the sun to be sphere, which is actually a good assumption. If you look at sun, it looks like sphere. Okay, so it's a good assumption, and I want to solve Einstein's equation outside the sun. That sounds like a relatively easy thing to do. So this is sun, and this is spherically symmetric. It is obvious. If you look at it, it looks like spherically symmetric. And therefore, you want to solve it outside the sun. So the first person who solved it, his name is Carl Schwarzschild, is a very famous astronomer. And he solved Einstein's equation while he was in the First World War, fighting with the, I don't know, French probably. Okay. And he solves Einstein's equations to obtain the gravitational field. And of course, in Einstein theory, the gravitational field means the space-time structure outside the spherical body like sun. And this famous solution is known as the Schwarzschild metric. And how does this Schwarzschild metric look like? This looks like this. If you want to test, of course, it's not easy to derive this Schwarzschild metric. If you want to test, put m equal to 0, where m is the mass of the central spherical object. You will immediately see that it goes to flat space-time metric. The presence of c square in the metric shows that this is a relativistic theory. Presence of g shows that we are talking about gravity. So this is a solution of a relativistic theory of gravity. Good. And it is believed that Schwarzschild solved this equation while fighting inside a tank. Okay, I don't know whether the story is correct or not, but he presumably died in the war. Not because of the war itself, he died because of I think typhus or something. Okay. Anyway, or in the context of solutions of Einstein's equation, I should also mention an Indian name, Professor P.C. Vaidya from Gujarat. In fact, he was the Vice Chancellor of the Gujarat University. Just like the Schwarzschild solution is a solution of spherical symmetry outside the sun, but it is assumed that sun is time independent. Nothing is changing. So Vaidya gave a solution for time dependent case, and this is what is known as the Vaidya black hole. This is widely used in the GR literature. It's a very famous solution. You should know that this solution is very, very important in understanding the properties of the black hole. And this is what this Vaidya solution represents. It represents matter accreting into the black hole and black hole radius increasing, where the Schwarzschild solution is the static, where nothing is going into the black hole. Okay. Now, given all those solutions, if you now look at the solution, you will see that there is a remarkable result. The remarkable result is that those solutions represent a kind of a radius r equal to 2gm by c square. Okay. It seems that if you cross that radius, the property of the solution says that you cannot come back. It's kind of a one-way membrane surface. It's not very problematic. If you calculate this radius for sun, the answer will be some 10 kilometers. Okay, so that means it is well within the sun. And I told you, Schwarzschild metric is only outside applicable. So that means we don't have to worry about Schwarzschild radius for sun. It is well inside the sun, where the solution is something else, because there is matter. But suppose you take the sun and you are very powerful and you squish the sun, say less than the Schwarzschild radius. Then Schwarzschild radius will be outside the sun, and then you should worry about the Schwarzschild radius, what happens at that state. So basically in that case, outside that small sun, which you have squished, okay, there is the imaginary surface. And if you cross that surface from outside, you will be never able to go out. And this is what we call a black hole. So mathematically, the Schwarzschild solution represents a black hole, but it seems for most of the star, it is not a thing which is physically interesting, because the Schwarzschild radius will be well inside the star. You need a giant which can squeeze the sun to a 10-kilometer radius. And what is a 10-kilometer radius? You know, this is like, you know, the distance between South Calcutta to North Calcutta. Okay, so you have to bring the sun as small as that radius. Okay, and then you will create a black hole. There is no such force, at least in our vicinity. So the question is this black hole, the existence of this one-way surface is only an academic curiosity, or there are some objects in nature? Then there are another Indian person, Subramaniam Chandrasekhar, while he was a graduate student in Cambridge, he proved a remarkable idea that no, there are forces in this nature, particularly from the stellar collapse, when the star, the nuclear fuel inside the star is got exhausted. It cannot remain stationary because of the gravitational force, and the gravity collapses the star onto itself, and this implosion ultimately can lead to the, for very massive star, can lead to the object called the black hole. So I should again mention that so the idea of Chandrasekhar is that massive stars die and they can indeed form black holes. In fact, I should again mention there is a very interesting old paper by B. Dept from Calcutta University, who actually analyzed the collapse problem even before the others like Oppenheimer and Schindler. So we should actually call it Dept, Oppenheimer, Schindler collapse. Okay, this is something I think at least Indian community should remember. Okay, so let's go ahead. So what we have found is that there are such objects in nature. It is physically possible. Of course, whether we see it in the sky or not is a different issue. But there is a physical model possible for such object where there is a one-way membrane outside them. Okay, the event horizon. Today we all know such objects exist. In fact, I'm going to talk about the experimental or the observational signatures of this object. But let's go ahead. Then it turns out that all those solutions of black hole exhibits a very, very bizarre property. It seems that at the center of the goal, there is always a space-time singularity. What does it mean? That take all those solutions, it seems at the center, the density, the curvatures, everything becomes infinite. So if once it becomes infinite, the mathematics of general relativity is incapable in handling those infinities. So it means that the theory itself is signaling something wrong is going on at the center of these holes. It is something akin to the Rutherford model instability. Okay, the Rutherford model itself signals that it is unstable. Okay, this instability itself comes from the predictions of that theory. Okay, so therefore it cannot be physical. Similar sort of things happening at the center of the black hole. There is a point at, I should not say point. Let's not be that technical. Let's call it point. Okay, there where the space-time curvature is infinite. Now, more mathematically, the singularity is the boundary of all observers, such as wall line cannot be extended any further. So it means that if you cross into the black hole, there is a point at which the wall line stops. The path stops. It cannot be extended. It seems that the whole structure of space-time becomes meaningless at that point. So the existence of singularity predicts that the classical general relativity must be modified at the center of the black hole. And it is now widely believed that there will be a quantum theory which will make the singularity vanish. But nevertheless, in classical theory, when people have found those solutions, okay, they found that, oh God, this contains singularity. And what the hell it means? How do we understand the singularities at the center of the black hole? Similarly, not only in case of black hole, it turns out if you solve Einstein's equation for the entire universe, this is what is called the cosmology. Okay, it shows that the simplest model of those solutions, where you assume that the galaxies are like non-interacting molecule, universe is like the galaxies do not interact, universe has no special position, no special direction, everything is homogeneous and isotropic, then you can solve Einstein's equation. And it seems they also predict that the past of this universe, there is a singularity. Okay, exactly is like the black hole singularity. Okay. It seems there are special solutions of general relativity, physically interesting, like black hole solution and the cosmological solutions, where there are singularities. There's a slight difference. Please understand, for a black hole, the singularity is in your future. If you fall into the black hole, you will hit the singularity in the future. For cosmology, the singularity is in your past. So if you go back in time, ultimately billions of years from now, billions, okay, 10 to 15 billion years from now, you will hit the singular past. Okay. Now, this existence of singularities is very, very disturbing. Now, obviously, the singularities are the breakdown of the classical theory. Now, the physicists, when they see problems in their existing theories, they don't give it away so easily. Okay. So first question they will ask, how generic are the singularities? Look, you have assumed spherically symmetric matter. You have assumed galaxies don't interact with each other. You have assumed universe is homogeneous and isotropic. So it could be this existence of problematic singularities are because of your stupid assumption. You should have assumed things better, do your calculation with realistic thing, and then you would have got the correct answer with no singularities. So basically what you need, tools to understand the nature of the solutions of the Einstein's equation. And as I told you, the mathematics is not that easy. We do not know the solution space of Einstein's equation once we go beyond the simplest setting of spherical symmetric or homogeneity and isotropic universe. Okay. Otherwise, we cannot answer this question whether the all solutions of Einstein's equation which has black hole are singular. This is very difficult to answer. And this is the beginning of the scientific life of Stephen Hawking. So all this background, unfortunately, is required to understand from where Hawking started. So let me again clarify the question. For black hole, the singularity is in the future. For cosmology, singularity is in the past. And the question what we have is that, is it the generally consequence of the Einstein's theory? See, nothing can be more fundamental than this question. Okay, it's asking whether Einstein's theory itself is consistent or it requires modification at the beginning of the universe and within the deep inside the black hole. Okay. So this is the beginning of the professional life of Stephen Hawking. When these calculations are there, people are trying to understand the generic properties of the singularity. Hawking entered into his professional life. Stephen Hawking came from a family of doctors, actually, and he begins his graduate work at this very famous campus of Trinity College in 1962. And his PhD advisor was also a very famous general relativist at that time, Dennis Stigma. And it was also at the same time when he was diagnosed with this motor neuron disorder, which is technically called the ALS disease. And ultimately, this is what led to his physical disability. As promised, I'm not going to talk about his personal life. They are very interesting, but nevertheless, I will focus mostly on his professional life. Let me go ahead. So this is the time where Stephen Hawking met with a very, very powerful and extremely meritorious British mathematician, Penrose. Okay, and this is their picture at the time when they met in 1960, and these are pictures few years ago in a birthday celebration of Stephen Hawking. You can see how they have matured, and they come up with an answer to this fundamental question. And this is what we call the Hawking-Penrose singularity theorem. What does singularity theorem say? Singularity theorems are technical in nature. I will just give you the hint of the content of the singularity theorem. What they say is that the singularities, in some sense, are the generic features of Einstein theory. They are not because you have assumed spherical symmetry or homogeneity and isotropy. It's not because of your assumption. Okay. See, sometimes assumptions can lead to very bad thing. All of you have studied the theory of force vibration. Okay. So if you assume there is no friction, you can show the resonance. Okay. At the resonance, the amplitude is infinity. Okay. Of course, it's a bad assumption. Once you assume that there is a drag, you can show no, the amplitude is not actually infinite, it's actually quite high, but limited by the drag. Okay. So one could be possible that this singularities, this infinities inside the black hole could be because of the bad assumption. Just like the resonance, infinity at the resonance is because of your bad assumption. Nothing is actually infinity because you cannot ignore friction or the drag or dissipation ever. Okay. But what Hawking and Penrose showed, that is not the case. So they shows given certain set of very reasonable conditions. Okay, so I'm not going to give the meaning of these conditions, but in some sense they are like there's a causality is true, energy is positive, something like that, and there is some very reasonable boundary conditions which they're quite reasonable within the mathematics, and then they show singularity is unavoidable in a gravitational collapse, and universe must have a singular past. These theorems are considered one of the greatest results in mathematical physics. The proof requires very, very novel global and topological techniques for pseudo-Riemannian manifold. Physicists first time saw these techniques. These were known to the mathematician to a limited extent, but these two people understood this mathematics and then bring it for the physicist and then gave us this proof of this theorem. The physical significance of this theorem is remarkable. Apart from the extraordinary mathematics, what they show is that Einstein's theory of general relativity cannot be the ultimate theory of nature. The predictability of physics demands that we must seek a quantum theory of gravity and get rid of these singularities. So nothing can be more profound than this, saying that the Einstein's general relativity, however great it may be, it is actually limited in its scope, and we must include new physics to get rid of the singularity and bringing out completely singularity-free description of nature. Of course, singularity theorem don't say how to do it. Rather, they say that we need to do it. Good. And I should say that just to give you a glimpse of what kind of mathematics is involved, you can go ahead, and this is a piece which I copy pasted from World. It is not easy to get trained to learn singularity theorems. So I wanted to impose upon you by this that what kind of devotion and work required for Hawking and Penrose at that time, learning completely new mathematics and then bringing it for the physicists. What they did is that they have changed completely the language which we speak to understand the laws of nature. The languages before Hawking and Penrose and after Hawking and Penrose is totally different. At this point, I must again mention a seminal contribution of Amal Kumar Raychaudhuri from Presidency College. Amal Kumar Raychaudhuri, just before the discovery of the singularity theorem, gave a very, very fundamental equation. So I've just written this equation, at least for the time-like case, whatever that means. This is the equation which tells you, in very simple sense, how two nearby particles move, whether they come very close to each other or go away from each other in a gravitational field. It turns out this equation is instrumental in proving the singularity theorem. You cannot prove singularity theorem without this equation. Okay, so we should know that this contribution is so significant in proving this fundamental theorem. Let's go ahead. So if you look at the Nobel Prize citation, of course, it is given to laws of Penrose for the discovery of the black hole formation is a robust prediction of the general theory of relativity. And this is actually an acknowledgement of the work by both Hawking and Penrose. And the Hawking's contributions to this work is also immense. The second part of the prize goes to Genzel and Gaze for the discovery of the observational signature of supermassive compact black hole at the center of our galaxy. Today, we know there are overwhelming observational evidence in favor of a black hole. There's a black hole shadow, there's a supermassive black hole at the center of the galaxy, various observations from X-ray to visible observation, then gravitational wave signature. All this observation cannot be explained together. One observation may be explained by non-black hole candidate, but together, black hole is the only consistent model we know which can beautifully explain all these observations. So therefore, most of the physicists are now convinced that black holes do exist in nature. And the fundamental theory of black hole, whatever we do today in our mathematics or in our simulation, in our observation, is actually broadly and very, very crucially dependent on this particular paper by Stephen Hawking. This is the classic paper where he wrote down the language, the mathematics required to understand the laws of black holes. And this is in 1971 in Communication and Mathematical Physics, and it's called Black Holes in General Relativity. This is a remarkable paper, and it's extremely important paper in any study, both theory and observation related to black hole. Among other extraordinary results, it also gave a famous, very, very important result, which says that area of a black hole cannot decrease. So what does it mean? Take two black holes. Let's say they have an area A1 and A2, mass M1 and M2. They collide, form a new black hole. Of course, we know that what will be the energy radiated? Final mass minus initial mass. Of course, there is a C square, which I have not written. Okay, so M3 minus M1 plus M2. That is the available energy which can radiate to as the form of the gravitational waves. This can be anything as long as you can make M3 as small as possible. Or you see what I'm trying to say, that you can get a lot of energy out of it. Okay, So it is radiated. So it actually there's a minus sign here, okay? Because I'm defining radiated energy, okay? But what Hawking said is that the radiated energy cannot be arbitrarily large. Why it cannot be arbitrarily large? Because he said black holes must obey a property that the final area must be greater than the sum of the initial areas. That constrained how much energy can be radiated. And it turns out that it gives the efficiency, maximum efficiency, which you can obtain in the form of the gravitational radiation, okay, from the black hole. So if you think of it, this is exactly like the second law of black hole thermodynamics. In second law of black hole thermodynamics, what second law of thermodynamics, it tells you, okay, I give you a certain amount of energy, but you cannot convert everything into work. Efficiency cannot be 100%. So therefore, there is a limit to the efficiency, which is the Carnot's efficiency. Okay. Exactly here, that is what similar thing is happening. The area increase theorem tells you that you cannot have 100% efficiency in converting gravitational energy into useful work. There's a limit. And that limit came from the area theorem. By the way, Rajchandra equation again plays a very, very important role in proving the area theorem. So area theorem says that there is a hint of thermodynamic behavior, as if the area of a black hole exactly behaving like the entropy. Entropy cannot be decreased. In any process, entropy will increase eventually, the total entropy. And exactly the similar thing happening for the black hole, the area is increasing. So this is the next paper, which outlines, as you can see, the laws of 4 laws of black hole mechanics. And it's quite interesting that if you look at the last line, it corresponds in some way, transcends the flow laws of thermodynamics. So Hawking, Bardeen, Carter, these 3 famous people, Bardeen and Carter are also very well-known general relativists, together proved that the laws of black hole mechanics has one-to-one correspondence with the laws of thermodynamics. So this is actually quite interesting that after this time, after this discovery, the natural idea was to propose that area is the entropy of black hole. Whatever that means is the next stage. But Hawking never proposed it. The history of science and the history of scientists is actually quite interesting that Hawking himself, although he has written this paper, never thought that entropy and area are related. So it's quite interesting that instead of Hawking, it was somebody else, Bekenstein at Princeton at that time. He took this bold step and he proposed that the concept of black hole entropy. And he said that black hole entropy must be proportional to the black hole area. Now, this is remarkable because think of it that in original gases, the entropy generally goes as volume. But for black hole case, the entropy goes as area. But then there is a puzzle. If black hole entropy goes as area, what about the black hole temperature? How can black hole have a entropy without having a temperature? But classically, temperature means that it must radiate. But we already know nothing comes out of the black hole. So therefore, the only temperature that thermodynamics allow black hole to have is absolute 0. It is a black, it cannot emit, so it sets the lowest possible temperature. It can only absorb energy from outside. So how it is possible that it can have entropy? This question, crucial question, was solved by Hawking, and this led to one of the most remarkable discovery of modern physics, presumably after general theory of relativity, at least in this last 100 years, and that is black holes do radiate. They do radiate, and they do radiate exactly like a thermal body with temperature capital T equal to CH cube 8 pi gm. M is the mass of the black hole. And of course, you can understand other fundamental constant. And once this is the result of the Hawking, where he proved that if black hole has an entropy, it must has a temperature, and they are related by a thermodynamic equation TdS equal to dm. Note first the presence of H bar, the quantum mechanics. So the Hawking temperature is a quantum mechanical result. It does not come from the classical general relativity. So therefore, it evades the classical property of one-way membrane of the black hole. Okay. Also look at this equations. Okay. All the fundamental constant known to man or human. Okay. The Boltzmann constant, c, the speed of light, Newton's gravitational constant, Everything is there in this equation. Okay. H bar, quantum mechanics. So in some sense, what we believe, these two equations are the first glimpse, the lowest order approximation of quantum gravity, the quantum theory of gravity, which is believed to be the theory of everything, okay? Or all interaction. By everything, I simply means theory of all interaction, at least the quantum theory of gravitation, okay? So these equations are remarkable equations. I mean, if you can write an equation where all the fundamental constants are there, I mean, that would be like a, really, really elegant equation. The only place I know that such elegancy comes is the Chandrasekhar limit, okay? Great. So this is the discovery of the black hole thermodynamics. And then, as I told you, what black hole radiation is a quantum process. Technically, Hawking showed us how to do quantum mechanics in the presence of black hole. And in some sense, in a heuristic sense, that Hawking radiation can be understood as a quantum tunneling phenomenon, but let me not go into this. It's a rather complicated thing. But Hawking radiation gave us a challenge. First question is that what is the microscopic origin of black hole entropy? Look, you have talked about entropy. Temperature of a gas inside a container is a manifestation of its molecular motion. So I understand the meaning of temperature at that stage because I know the microscopic degrees of freedom. So the question is, what are the microscopic degrees of freedom for black hole? What are the things which is oscillating and giving, in some sense, giving you the black hole entropy? So what you are looking for, microscopic structure of the space-time itself. There is a plausible answer which string theory provides because of work by Ashok, Strominger, Bafa, and they have actually calculated in certain models of string theory, the microscopic origin of the black hole entropy can be calculated up to all factors. For example, this factor, where is that factor? Yeah, look at this 1/4. That's the factor which everybody wants to calculate, okay? And it turns out in string theory, you can actually calculate this factor, but for very, very special black holes, okay, in different dimensions, okay? But more than that, there is also another challenge. This is what we call the challenge of the black hole information loss paradox. So black hole emits radiation and its mass decreases. Remember, the temperature is the inversely proportional to the mass. So more it's hot, mass decreases, temperature increases more. It's a runaway process. So black hole has a mass, it radiates, it mass decreases, it radiates more. Mass decreases, radiates more, mass decreases, and ultimately what happens? What is the end stage of the black hole evaporation? Is it just thermal radiation? The black hole completely evaporates from our space-time or the universe? Now this is very, very interesting, okay? Because it only emits thermal radiation. The thermal radiation is just function of total mass. I'm ignoring angular momentum and everything. The temperature of the thermal radiation is the only number I required to understand that radiation. And it is independent of the details of the black hole. So for example, you can start with a chair of mass m, collapse it, form a black hole, it radiates, it gives you a thermal radiation of 1/8 pi m. I set C, G, everything to 1. You take a monkey of same mass of the chair. I was thinking of two things. I think it is possible to have a monkey and a chair of same mass. I may be wrong, okay. I don't know how to weigh them. So take a monkey with some mass m, collapse it, form a black hole, if you can. It Hawking radiates, it gives you only thermal radiation of the same temperature. So by looking at the thermal radiation only, you have lost all information, whether you have started with a monkey or a chair. And this is what famously we call the black holes are ultimate information eraser. So this is the paradox, because what is happening is that every information of the initial state is completely destroyed by this process. This cannot happen. And in fact, in quantum mechanics, there are rules which says that it cannot happen. So therefore, it's a paradox that quantum mechanics in the presence of black hole seems to violate the conservation of information. It's a very, very hotly debated topic in physics. Understanding the last stage of black hole decay is a challenge to all proposals of quantum mechanics and quantum gravity. In fact, in last few years, there are very, very interesting development related to the black hole information loss paradox. But anyway, that's I don't want to discuss. Good. So I should tell you that all this came, so everything is coming from the Hawking's discovery, the greatest discovery of our lifetime, maybe one of the greatest, definitely. In fact, even in as late as 2016, Hawking is so active. So one of the way to solve information loss paradox is what is called putting some soft hair on black holes, whatever this chapter means. But look at this paper where Hawking is also a co-author with Perry and Strominger. These are very well-known general relativists and string theorists. This is as late as 2016. Okay. So Hawking proposed in this paper a new way of resolution of the information loss paradox. I don't think it's a correct way, but nevertheless, it's a very, very interesting way. It shows how active that person is. Okay. So what do we learn from the life of Hawking? The extraordinary discoveries. Okay. So Hawking's life gave us extraordinary ideas of our time, from the dawn of the universe to the end of the black hole. See, all of us have our mundane life. Okay. Whatever we do, we have our own, our own vices. We have bad things for each other. Everything we do, there are good things and there are bad things. But at some times, when you look at these bigger questions about the universe, that gives us a sense of insignificance compared to the scales of the cosmos. But at the same time, enable us, give us power that we can still, being so insignificant compared to the universe or the black holes, those processes, we can still at least hope to understand them. And the Hawking's life is a testimony of this being so significantly insignificant. Okay, I find it remarkable, actually. In fact, there is a very interesting quotation by none other than the Bernard Shaw on Albert Einstein. So let me tell you the quotation. So quotation is actually on the Einstein, where Bernard Shaw says that Napoleon and the great men were the makers of empires. So there are these great men in history, like, take any name, Alexander, Napoleon, okay? They have created great empires. And those empires, they have, they like stayed for years, okay, with them. But there are another group of people, as Bernard Shaw pointed out, okay? Another group of people are people who have never had an empire, but they had universe. Ptolemy had its own universe. That universe was our universe for more than 1500 years or 1400 years. We all thought that we had believed in the universe of Ptolemy and Aristotle, whatever. Newton also created his own universe. And that universe lasted for Albert Einstein for 300 years. More than 300 years, we thought that our universe is Newtonian. Einstein made a universe, the general relativistic universe. And of course, Bernard Shaw commented, we can't tell that how long that it will last. And we all know the answer, that Hawking has proven that the fact that Einstein's universe is only limited and there's a beyond life, beyond the Einsteinian universe. Now, today, we actually live in the fascinating universe of Stephen Hawking. Can you imagine that the glory that these people, through their mental ability, can give a meaning to the fundamental laws of nature, which obey, the universe obeys, okay? So we now live in the fascinating universe of Stephen Hawking. It is a universe with black holes radiating and time extending to the singularity. It is a beautiful melancholy of the laws of nature, and it's a pursuit, as I pointed out, to understand the ultimate law of nature. So what we believe that there will be another genius, maybe somebody from these students who are listening to the talk will prove that Stephen Hawking's universe is also limited, and they will create their own universe where we will happily live. So I'll end with this quotation from Hawking. This is a very, very famous quotation, but nevertheless, I want to use this quotation and at least read this quotation because this is actually quite remarkable. It is from his book, Brief History of Time, where he says at the end, if we do discover the complete theory, it should be in time be understandable in broad principle by everyone, not just by few scientists. In fact, I believe it is the duty of scientists to make it comprehensible to the rest of the people. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of the question why it is that we and the universe exist. If we find the answer to that, it will be the ultimate trump of human reason. For that, we would know the mind of God. Thank you.
Thank you. Thank you, Dr. Sarkar. It was such a fascinating and intuitive talk. You not only talked about Hawking's universe, you also gave us a glimpse about the Newtonian, the Einstein's theory of gravity. You gave us a general idea, overall idea about the black hole. But what fascinated me is how you intertwined the collaboration, the contribution of our Indian scientists with your talk, and that must have inspired our students. You spoke about Vedya metric, you spoke about Chandrasekhar limit, you spoke about the contribution of Amol Kumar Roy Chaudhary. You also spoke a bit about contribution of Ashok Sen, I believe, and I'm sure, and you ended in a very positive note that maybe one day our students will find their own universe. And to that, on that note, I would now go to the question answer session, and to conduct the questions, I would request Dr. Proshunno Mondol, one of our faculties in Department of Physics, to please conduct the question answer session with Dr. Sarkar. Over
And a
to
very
you.
good friend of me.
Yes,
A very good friend of me.
yes. So over to you, Proshunno. Are you there?
Yes. I think I am audible.
Yes, Proshunno.
And thank you, Aditi, for for giving me this opportunity. And thank you very much, first of all, to Dr. Sarkar for his wonderful talk. And he already has mentioned that we are a very good friend. Actually, we actually did our BSc and MSc from the same college and same university, actually. So in this talk, from this talk, we got to know many things about the theory of gravity, black hole, and also work of Einstein, Hawking, and many other scientists. I must say that Dr. Sarkar have clearly explained many things in this very short time. And we have received many questions from during the registration itself. We also have questions from the Zoom chat box and also the chat box of the YouTube live stream. So maybe I will ask a few questions very quickly because we are running short of time. So if you are ready, Dr. Sarkar, I can start. Okay. Okay. So the first question, it is actually from the registration. During the registration, one of the participants asked that why theorem of Hawking radiation is not enough for connecting general theory of relativity and quantum mechanics.
Okay, so technically, the way Hawking radiation is calculated is like this. So I'll give you an example from your undergraduate quantum mechanics. Okay, so you have studied the energy levels of the electrons. Okay, you have also studied how energy levels of electrons interact with the radiation. For example, when you derive the perturbation theory or everything, the atomic transition states. In those calculations, you have always assumed that the electron is a quantum particle which has quantized energy level. But in many of the cases, mostly it is assumed that the radiation is classical, described by a classical field of Maxwell's electromagnetism. Okay. So this is what we call the semi-classical approach. The Hawking radiation is derived also a similar semi-classical approach, where what one do is that consider the gravity or the black hole's spacetime to be a classical system. And on this classical system, you consider quantum fields like a scalar field or whatever. Okay, you can think of a quantum particles. Okay, and study the dynamics of this scalar field or the quantum theory in the presence of a classical black hole. So it is not quantum gravity. This is a semi-classical gravity. But also we know that many of this analysis of the atomic transitions using semi-classical gravity can actually give you more or less good result. Even if when you do the full quantum theory with quantum electrodynamics, when you quantize the radiation also, at least the leading order term is exactly same as that obtained of the semi-classical gravity. So this is exactly true for Hawking radiation also. What he believes that if we had a quantum theory of gravity, at least the leading order approximation of that quantum theory of gravity will be something like a Hawking radiation. So therefore, it is not full quantum gravitational result. Nevertheless, it's a step towards the quantum gravity.
Okay, thank you. Maybe I can now take a question from the chat box. So one of the participants asked that why do scientists have so many doubts about multiple universe?
Okay, by the way, scientists have doubt about everything, not only
Yeah,
as one
yes, yes,
universe.
yeah.
And it is the scientific approach and the scientific methodology which says that we do not believe things so easily. Just because Einstein said or the Hawking said, we do not believe. The science does not work on authority. So therefore, the multiple universe is a remarkable theory. It's a remarkable theory because it aims to solve certain very, very conceptual problems. And also in string theory, it seems suggestions, although many string theories also disagree with this, that the ground state of the string theory is not unique and there could be many, many possibilities. Though it gives you very, very interesting solutions of certain cosmological problems, it also raises this question. Not only that, how do you even detect the multiverse observationally? So the falsifiability of this concept is not very clear. In my personal opinion, I believe falsifiability is not always the good measure for the laws of physics, but that's a separate argument. But we don't have any observational evidence in favor of the multiverse. So before observational evidence is just another theory. Very, very interesting theory, plausible also in my personal opinion, but nevertheless, it's still an unproven hypothesis. So therefore, it is good that we doubt it.
Okay. Now I probably will ask the last question. It is also from the chat box, and it is not really a question. It is rather a query. It is one of the participants asked that I have heard that the first concept of black hole was first given by S. Ramanujan completely on mathematical basis. Is it correct?
I have no idea. I don't know, at least I never heard of this. It is unlikely because Ramanujan was interested in, the mathematician Ramanujan was interested in completely different thing. And at least not that I am aware of.
Oh, okay. Maybe I can ask one last quick question about it is from the registration. It is the participant asked that where the expansion of the universe will stop.
Good question. Okay, so it depends on the content of the universe. Okay, so for example, we believe that the universe contains something called dark energy. Okay, the dark energy is, or in mostly believed to be the cosmological constant, is something which works in very, very lucid sense against the gravity. It's kind of an anti-gravity. If this hypothesis of the existence of dark energy is the correct, that universe expansion will never stop. It will expand forever, and rather it will accelerate. Okay. So the state of the universe in distant future is like everything is separated from everything. Okay. So, but if the dark energy is just our illusion and we are making a mistake in our observation, which is, unlikely, but it's still possible. Okay. In that case, it depends on what is the content of the universe. See, there are two basic ideas. There is a universe is expanding and gravity is trying to pull it down. Okay. So this is a competition between these two forces. The tendency of the explosion started with the initial Big Bang and the gravitational attraction. It is the content of the matter which decides which one will win. So this is a question which, at least today, it seems it will never stop.
Okay, thank you again, Sudipta. Now I can hand it over to Aditi again. And thank you again, Sudipta.
Thank you, Prasanna. Thank you for taking the pertinent questions. I could not have done it. And now I would, for the participants, the feedback link is given in the chat box. I would request you to fill up the feedback link and you will get the certificates within a week. So to give a vote of thanks, I would now request our IQSC coordinator, Dr. Suchandra Chatterjee, to please deliver the vote of thanks. Over to you, Suchandran.
Thank you, Aditya. Am I audible?
Yes, yes.
So, a graceful evening to our honorable speakers, valued viewers, worthy members of Surendranath College family, all the dignitaries, and my beloved students who have virtually gathered here today for this one-day national level webinar organized by Department of Physics, Surendranath College under DBT-Star College Strengthening Scheme. You know, the essence of all beautiful art is gratitude, and no duty is more urgent than that of returning thanks. So I feel myself really privileged to get this golden opportunity to propose a vote of thanks for today's fantastic presentations, valued presence, patient hearing, and all those real hard work behind the scene that made this webinar a reality. On behalf of DBT-Star family of Surendranath College, first of all, I extend a really hearty vote of thanks to both the esteemed speakers today, Dr. Subhaditya Bhattacharya and Dr. Sudipta Sarkar, for gracing this occasion, sparing their most valuable time from their busiest schedule. Dr. Bhattacharya and Dr. Sarkar, I do sincerely hope your most eloquent, crisp, and informative speech has definitely enriched all the students and faculty members alike to get an idea about dark matter and black holes and an overview of Hawking's universe. My sincerest gratitude to both of you, sirs, for revealing some quiet truth about those mysterious dark matter, black holes, and the universe as a whole. Thanks a ton for emphasizing on the very fact that we now live in the fascinating universe of Stephen Hawking and someday may live in a different universe, completely different universe of someone else. Thank you, both of you, once again. My heartfelt gratitude to DBT Department of Biotechnology, Government of India, for awarding us this grant. We are really indebted to them. I'm sincerely thankful to our respected principal and honorable members of our governing body and IQAC for their inspiration and support. Thanks are due to all the faculty members of Physics Department and the other 3 departments of this family for their tireless effort and enormous cooperation. I'm really short of words for the involvement and dedication of the technical team members for their willingness to take on the completion of tasks beyond their comfort zones, even in this difficult time. Kudos to them. Thanks are due to all my amazing colleagues, both teaching and non-teaching, who always stand by us, motivate, and cooperate. I extend my most sincere love to all our beloved students from various institutions. Their colorful presence has definitely made this webinar even more meaningful, even more memorable. Last but not the least, valued viewers, we owe you a lot for witnessing this program to make it a resounding success. Without your active participation, this event could not have been successful. So a very big thank to all of you. Now it's high time to conclude. Hope to meet you all in similar programs in this very platform very soon. Till then, all stay safe, stay healthy. Thank you one and all. Thank you very much.